Hello, this is EEE 41 Lecture 2 Problem Solving. So before we start with the problem solving, let's just review first some of the equations we've introduced so far. So we have this general form of the charge neutrality equation, which is true for our semiconductors. So the ones on the left, Nd plus and P, are the positive charges in the semiconductor, while Na minus and N on the right are the negative charges. So the number of positive charges must be equal to the negative charges, and therefore the semiconductor must be charge neutral. We also have the law of mass action, which states that Np is equal to Ni squared. However, this is only true for materials in thermal equilibrium. Now, if we combine these two equations and assume as well that total ionization is true, so we just convert Nd plus to Nd and Na minus to Na, then we'll end up with these two equations here. And we'll use or these two equations can be used to calculate the carrier concentrations given the doping concentrations and the intrinsic carrier concentration. However, again, just like the two, we must meet the conditions that the material must be in thermal equilibrium and under total ionization. If it is not in total ionization, then we'll just replace back Nd with Nd plus and Na with Na minus. Now, under usual conditions for N-type, so we have N is approximately Nd, and by law of mass action, P is approximately Ni squared over N. But since N is already approximately Nd, then P is just approximately Ni squared over Nd. So this equations here, aside from being in thermal equilibrium and total ionization, assumes that Nd minus Na, so the doping concentration, must be much greater than 0, or that Nd is much greater than Na, which is usual for N-type semiconductors where there are actually no acceptors, but we'll have to make sure that Nd is very large. And also, Nd minus Na must be much greater than Ni. So for P-type, the one here on the right, we can say that we can start with P is approximately Na, and then with law of mass action, N is just Ni squared over P, but P is already approximately Na, so N is just approximately Ni squared over Na. So this one assumes that Na minus Nd is much greater than 0, and also Na minus Nd is much greater than Ni. Let's start with problem 1. So for problem 1, we are given that a piece of silicon at room temperature was measured to have an electron concentration of N is equal to 5.4 times 10 to the 5 per cubic centimeter. And the semiconductor was known to be doped with one type of dopant only. And the questions are, what is the whole concentration P for the material? We'll also have to determine the semiconductor type and calculate the doping concentration. So for the first question, what is the whole concentration? So note that we are given a piece of silicon at room temperature. So for this material, we have Ni is equal to 10 to the 10 per cubic centimeter. And we are also given this N right here. And so, assuming that the material is in thermal equilibrium, since none is mentioned, we can assume that the material is in thermal equilibrium. If we are asked what is the whole concentration, we can simply use the law of mass action. Np is equal to Ni squared, and given Ni, or knowing Ni and given N, we can solve for P. So P is just Ni squared over N, so 10 to the 20 over the given N, which is 5.4 times 10 to the 5, and we should be able to compute 1.85 times 10 to the 14 per cubic centimeter for the whole concentration. So we're already okay with the first problem. The next, we have to determine the semiconductor type. Now, just a review. An N-type semiconductor is one where there are more electrons than holes. A P-type semiconductor is one where there are more holes than free electrons. So for this case, we have more holes. So P has a multiplier of times 10 raised to 14, whereas the electron concentration N is just on the range of 10 to the 5. And therefore, we must be able to conclude that since P is greater than N, then the material must be P-type. And should now be able to answer, or we have already answered the second question. So for ease of reference, we just extracted the most important information from the given. So we have silicon at room temperature, N is equal to 5.4 times 10 to the 5, and we've actually already able to compute that P is equal to 1.85 times 10 to the 14, and that the material is P-type. So the next question is, what is the doping concentration? So going back, we have identified some quite long formulas relating the carrier concentration to the doping concentration. So N is equal to Nd minus Na over 2 plus square root of Nd minus Na over 2 squared plus Ni squared. However, there are simplifications for P-type where P is approximately Na. Now, can we use that approximation? So the requirements for that approximation is that Na is much greater than Nd, and Na minus Nd is much greater than Ni. Now, since none is mentioned about the material having two types of dopants, then in this type of problems, we can safely assume that there is only one type of dopant in the system. So unless otherwise specified, we can assume that there is only one type of dopant. So in this case, since we've already established that the material is P-type, we can actually assume that Nd is simply 0. So next we ask, is Na much greater than 0? Now, we actually ended up asking that question since we want to use the formula or the approximation that P is approximately Na. And we can only use that given these assumptions. So if we assume that we can use that, then verify the assumptions, then the question simply translates as, is P much greater than 0? Is yes, is P much greater than 0? So P is 1.85 times 10 to the 14, and yes, it is much greater than 0. So the next question um, is Na, which we are now assuming that is approximately P, much greater than Ni. Now we have here silicon at room temperature, so Ni is again 10 raised to the 10. So the question is just, is P much greater than Ni? So since P is 1.85, then we can consider that yes, it is much greater than 10 to the 10. And that verifies that we can actually use the approximation that P is approximately Na. And from that, we already have the value of P, and it just follows simply that Na is approximately 1.85 times 10 to the 14. Now, if you're not very much comfortable with that um, flow of logic, then you can go for the longer route, which is to first again assume that there's only one type of dopant in the material. So since the material is p-type, assume that Nd is equal to 0, then use the long formula. So the long formula for P is Na minus Nd over 2, but Nd is assumed to be 0, so we're left with Na over 2 plus square root of Na minus Nd over 2 squared. So again, Nd is equal to 0, so that just simplifies to Na over 2 squared plus Ni squared. And with this formula, P is already known, Ni is already known, and therefore one must be able to solve for Na. Note, however, that if P is not much greater than Ni, then we cannot use the approximation that P is approximately Na, and therefore this long formula here must be used. And as a last note, note that the material is P-type, and we use this formula for P. However, we also have the equation for N, where again, if we use Nd is equal to 0, we'll just remove this one, and we'll have an equation in terms of N, which is known, Na, which we are trying to solve, and Ni, which is also known. However, it is suggested that you try to avoid using any of these equations if they are for the minority carrier concentration. So for this problem, we are considering p-type, so we use the formula for p and try to avoid using this formula. Okay, so we'll normally use this formula first for P, and then simply use the law of mass action for the minority carrier concentration. So on the other hand, if you have an N-type semiconductor, then use this formula first before trying to use this formula. So the version for the minority carrier concentration must be the last resort in terms of computation. So to summarize our answers, for this given, what is the whole concentration P? So we were able to solve P is equal to 1.85 times 10 to the 14 per cubic centimeter, and that is from the law of mass action, and P is equal to Ni squared, which works for materials under thermal equilibrium and not necessarily intrinsic. So here we know that N is equal to 5.4 times 10 to the 5, and we have silicon at room temperature, so we know Ni is 10 to the 10, so we can solve for P. So the next one, what determine the semiconductor type, we were able to show that this material is p-type since p is greater than n. However, if we still haven't solved this value for p, we can actually also deduce that the material is p-type from the fact that n is less than ni. So for a pure semiconductor, an intrinsic semiconductor, n is equal to p is equal to ni. For a p-type semiconductor, p is greater than ni and n is less than ni. And given only that n is equal to 5.4 times 10 to the 5, comparing that to 10 to the 10, then we can already say that the semiconductor must be p-type. So lastly, what is the doping concentration? We were able to show that we can assume that Na is approximately P, since P, the one we solved, is much greater than Ni. And we just forgot to include in our analysis that it was also given that the semiconductor was known to be doped with one type of dopant only. So given that it is p-type and it is doped with one type of dopant only, this justifies what we did, that Nd is equal to 0. However, in the future, when we are not, even if this is not specified, say we have a p-type semiconductor, we are given the value of Na, we can just always assume that if none is mentioned about Nd, then assume that Nd is equal to 0. And for N-type semiconductors, if none is mentioned about acceptor dopants, then simply assume that Na is equal to 0. Okay, problem 2. So for problem 2, we are given a silicon slab at a temperature of 450 kelvins is doped with boron at a concentration of 1.5 times 10 to the 15 per cubic centimeter, and with arsenic at 8 times 10 to the 14 per cubic centimeter. For silicon at 450 kelvins, use Ni is equal to 5 times 10 to the 13. So the questions are, is the material N-type or P-type? We also have to determine the electron and hole concentrations, calculate the total impurity concentration, and identify what is the minority carrier concentration. So for the first question, is the material N-type or P-type? So note that for this problem, we are given two dopants in the form of boron and arsenic. So note that boron is a group 3, so therefore it is an acceptor dopant, while arsenic is from group 5 and therefore it must be a donor dopant. Now looking at their values, since boron is the acceptor, so we'll use Na is equal to 1.5 times 10 to the 15 per cubic centimeter. While for arsenic, since it is the donor, then Nd must be equal to 8 times 10 to the 14. Now, it turns out that we have both acceptor and donor dopants in this material, but note that the doping concentration for boron is greater than that for arsenic, or Na is greater than Nd, since the multiplier for Na is 10 to the 15, while for Nd simply 10 to the 14. And with that, we can conclude that the material must be a p-type semiconductor. Note also that the temperature in consideration is 450 kelvins, which is greater than room temperature. And since we can already assume that total ionization happens at room temperature, then more so at temperatures higher than room temperature. Okay, so in this case, we can still assume that total ionization happens even if it is not in room temperature. So the problem is actually more complicated if the material is at a temperature below room temperature, because in that case we cannot be sure if total ionization would still hold. But for this case, we can assume total ionization. So we simply extracted the important information from the problem here, and also to save space. So we have silicon at 450 kelvins. We were told to use Ni is 5 times 10 to the 13. We were already able to conclude that Na is 1.5 times 10 to the 15 from the boron, and Nd is 8 times 10 to the 14 from the arsenic. And since Na is greater than Nd, then the material must be p-type. So given this information, we'll determine the electron and hole concentration. So we cannot actually go directly to the law of mass action, Np is equal to Ni squared, because there are two unknowns, N and P. Also, note that Na is not much greater than Nd, so the values are quite close. So we cannot assume that P is approximately Na just because the material is p-type. So we'll actually have to use the long formula for P. And so the material is p-type, so we can actually start with holes. So we'll start with the formula for P, Na minus Nd over 2 plus square root of Na minus Nd over 2 squared plus Ni squared, where we already know the values for Na, Nd, and Ni, but take note that we'll not use 10 raised to the 10 for this case, but rather use 5 times 10 to the 13. So we substitute the values for Na, 1.5 times 10 to the 15. And then for Nd, 8 times 10 to the 4. And then for Ni, 5 times 10 to the 13. And using our calculators, we must be able to solve that the whole concentration for this material, which is at 450 kelvins, silicon at 450 kelvins, must be 7.036 times 10 to the 15 per cubic centimeter. And with that, we have actually already computed the whole concentration. So the next one is for the electron. So we just included here the value we have solved for P, 7.036 times 10 to the 15. Now we can actually use the long formula for N, but it is recommended that we just use the law of mass action after solving for P to make life easier. So Np is equal to Ni squared, and therefore N is equal to Ni squared over P. Ni is equal to 5 times 10 to the 13, so we square that and divide by the value for P, which is 7.036 times 10 to the 15, and end up with this value, 3.553 times 10 to the 12 per cubic centimeter. And so we are now able to solve also for the electron concentration. For the next question, we are asked what is the total impurity concentration. So note here that we are asked the total impurity concentration. So we simply add Na and Nd and not P and N. So the impurity is given by Na and Nd, and P and N simply is the carrier, or are the carrier concentrations. So if we add, Na is equal to 1.5 times 10 to the 15 and Nd is 8 times 10 to the 14, then the total impurity concentration must be 2.3 times 10 to the 15 per cubic centimeter. Note that although carrier concentrations depend on the net doping, so in our formulas Na minus Nd or Nd minus Na, some material properties depend on the total doping concentration. So we'll encounter those or we'll discuss those material properties in the next lectures. For the last question for this problem, we are asked, what is the minority carrier concentration? So to be clear, N and P are what we call carrier concentrations. So free electron carrier concentration and whole carrier concentration. But specifically, we are asked, what is the minority carrier concentration? So for a semiconductor material, the minority carrier concentration is just the carrier concentration that is smaller. So for a p-type material, so since we have already established that this one is a p-type material, the minority carriers are the electrons, and we'll just need to answer that the minority carrier concentration is N, and we already have that value 3.553 times 10 to the 12 per cubic centimeter. So to summarize, in this problem, we were asked what is the material. Is it N-type or P-type? So we were able to conclude that it is a P-type since the acceptor dopant concentration from boron is greater than the donor doping concentration from the arsenic. We were able to compute for the whole concentration first, since this is a p-type semiconductor, and we use the long formula. And we use the long formula because we cannot say that Na is much greater than Nd. Now, after solving for P, we were actually also able to solve for the electron concentration using the law of mass action. The total impurity concentration is simply the sum of Na and Nd, and the minority carrier concentration is simply N, since this is a p-type semiconductor.